The traditional North American power grid operates on a massive, centralized hub-and-spoke model. Giant generation facilities, like this centralized power station, produce electricity at a massive scale. While this legacy architecture offers economic efficiency, it creates an inherently fragile infrastructure. If the central plant or a key high-voltage node goes offline, the entire downstream network goes dark. To reach residential areas, that electricity must travel hundreds or even thousands of miles across exposed transmission lines. In recent years, the escalating frequency of climate-induced disruptions has exposed the structural weakness of this system. Large-scale wildfires increasingly threaten and sever these distant, vulnerable connections. Extreme weather events, such as severe ice storms, routinely cause cascading blackouts across residential streets. The centralized grid cannot quickly isolate or repair these localized failures. As long as neighborhoods are structured merely as passive load sinks terminating at the end of a long transmission line, they remain fragile and dependent on distant infrastructure. The engineering solution to this vulnerability is the microgrid, a localized, self-sufficient energy island capable of generating, storing, and managing its own power. The hardware to build these systems has existed for years, yet deployment is consistently blocked by two specific factors: the complex physics of reverse power flow and the legal monopolies held by traditional utilities. Oregon is actively dismantling these barriers through two pieces of legislation: House Bill 2065 and House Bill 2066. These laws require the state to draft clear regulatory pathways, allowing local communities to legally plan, own, and operate their own decentralized energy systems. The Oregon Public Utility Commission, or OPUC, is tasked with translating these laws into an actionable framework. This official order establishes the initial rulemaking process to govern these new networks. These laws provide the legal authority for neighborhoods to transition from passive consumers to active local producers. Transitioning an entire regional grid to decentralized power is an engineering and contractual minefield. To manage this complexity incrementally, the OPUC utilizes microgrid archetypes developed by the Pacific Northwest National Laboratory. The simplest of these is the Level 1 archetype, a single customer system with behind-the-meter assets like rooftop solar and a home battery. Clear regulatory pathways for Level 1 already exist. The OPUC's immediate strategic regulatory target is the Level 2 microgrid. This table outlines the focus for the initial phase: campus-style systems with multiple buildings and a combination of behind-the-meter and front-of-meter resources. A Level 2 microgrid encompasses a single customer campus environment. It links multiple buildings, a shared solar array, and a central battery bank into one coordinated system. The critical boundary in this environment is the point of common coupling. This electrical demarcation line dictates which hardware is considered front-of-meter, interacting directly with utility infrastructure, and which is behind the meter, operating privately on the customer's side. Targeting Level 2 allows regulators to systematically isolate and solve the technical challenges of integrating front-of-meter and behind-the-meter assets. It establishes the necessary groundwork before they attempt the severe contractual complexities of a multi-customer Level 3 area microgrid. Under standard conditions, grid-tied solar systems are programmed to automatically shut down during macrogrid outages. This prevents dangerous electrical backfeed from injuring utility crews repairing the lines. Achieving actual resilience means overcoming this limitation. Microgrids must utilize technology that is grid-forming rather than just grid-following. When a macrogrid disruption occurs, a local controller immediately senses the voltage drop and triggers a physical disconnection switch at the point of common coupling. This physically isolates the campus from the failing wider network. Once isolated, grid-forming inverters take command. They draw direct current from shared energy storage systems and convert it into a localized, highly stable 60 Hz frequency and alternating current voltage to keep the campus running. The duration this isolated campus can survive depends entirely on the size of those shared storage systems. Sizing the battery bank is a precise mathematical calculation. The required battery capacity is calculated by multiplying the average daily load by the desired number of days of autonomy. That figure is then divided by the battery's maximum depth of discharge, multiplied by the round-trip efficiency of the inverter and storage system. Implementing co-housing principles or shared resource community designs drastically reduces that baseline daily load. When a community shares major appliances and resources, the required battery capacity drops, significantly altering the math in favor of the microgrid. The physics of islanding is a highly solvable hardware and math equation. The true barrier preventing wide-scale deployment has always been securing legal permission. The primary legal obstacle for these projects is the utility interconnection queue. Historically, neighborhood energy projects stall for years awaiting required feasibility studies, delayed by a limited number of utility engineers. House Bill 2065 eliminates this bottleneck. As outlined in the interconnection requirements of the new framework, the law establishes a statutory right for applicants to use certified third-party consultants to conduct these required studies. Furthermore, it mandates that utilities provide timely technical grid data to these outside engineers, effectively decentralizing the approval process. Once a system is approved to connect, the next major hurdle is financial. How do microgrids get compensated for the stability they provide to the wider grid? House Bill 2026 tasks the OPUC with establishing a new compensation and cost allocation methodology that recognizes the value of microgrid services. A key component of this new framework is defining the value of lost load. Regulators must determine how to compensate microgrids based on the avoided economic costs of a blackout, shifting the financial model from basic energy generation to actual resilience value. The framework also explicitly protects the integration of front-of-meter energy resources, even if those resources are owned by third-party developers or local municipalities rather than the utility. Together, these legislative tools break the traditional utility monopoly on distribution engineering and infrastructure valuation within designated zones. These regulatory frameworks are not purely theoretical. They map directly onto active physical pilot architectures operating across Oregon. The PAE Living Building in Portland serves as a prime example of an urban network behind-the-meter microgrid. Downtown areas utilize a network grid topography. These highly reliable networks are not designed to handle reverse power flow from distributed generation. Pushing too much power back trips protective relays on network transformers. To solve this, the PAE microgrid utilizes dynamic load curtailment. A sophisticated controller artificially caps its energy export to exactly 49 kilowatts, ensuring it never exceeds utility limits, even while islanding critical circuits internally during an outage. Contrast this dense urban model with the SC Salem community microgrid, which relies on a distributed front-of-meter architecture. The Salem project decouples generation from storage. It utilizes a city-owned solar array on a municipal building to charge a geographically separated, utility-owned smart battery. They operate as a single controllable system to provide emergency power to a cluster of vulnerable residential apartments. These contrasting pilots prove that the state's regulatory framework allows decentralized resilience to be precisely customized for both dense urban networks and distributed municipal topographies. Engineering grid resilience requires a structural and legal overhaul of energy management, as simple solar additions are insufficient to solve the isolation problem. Traditional investor-owned utilities continue to resist this shift, citing safety risks regarding third-party operation and concerns over cost shifting onto non-participating ratepayers. Despite this friction, the OPUC framework mandates cooperation between utilities and local governments, decentralizing the control of neighborhood power assets. The ultimate goal is to scale these isolated solutions. By connecting individual Level 2 campus nodes across a wider geography, the grid transitions from a vulnerable centralized hub-and-spoke model into a resilient interconnected web. By methodically solving the engineering and legal constraints of the Level 2 campus model first, Oregon establishes unbreakable precedents for hardware safety, third-party engineering rights, and fair compensation. This phased policy framework establishes the standards for safety, engineering, and compensation required to integrate multi-customer grids into a decentralized power network.